Hi, everybody. Thanks for being here, particularly after lunch. So, yeah, the title of the talk is Spectral Independence Beyond Uniqueness. So I'm going also to cover some parts about spectral independence in uniqueness region in a bit slower pace than what we discussed yesterday, just for the sake of completeness. Right, but generally the idea is to move also like the next step compared to what we discussed yesterday. Okay, okay, something doesn't work. Okay, so main object in this talk is Gibbs distributions, right? So for us, this is going to be distributions on combinatorial structures defined with respect to some graph G, right? So we have examples like the Ising model, the hardcore model, Nome-Dimer model, Q-coloring model, and a lot of other distributions have been mentioned during previous talks. In this talk, we mostly focusing on the Ising model and the hardcore model, like yesterday. So let me remind you what is this Ising model in the way I'm viewing it. So given some graph G, the Ising model is a distribution over assignment on the vertices of the graph, plus minus 1. We have these two parameters, beta and lambda. Beta is usually called inverse temperature. Lambda is the external field. This comes from physics, of course. Ising model tells us that the configuration sigma, the assignment of plus minus 1 to the vertex of the graph, is assigned probability measure mu sigma, which is proportional to this weight here. What is this weight? Is beta, the inverse temperature, right, to the number of monochromatic edges in sigma, right? So monochromatic edge is an edge with plus plus or minus minus, right? So beta is right to the monochromatic edges times lambda, the external field, rise to the number of vertices with assignment plus other sigma, right? And in order for this weight to become probability, we need to divide with some normalizing quantity, right? And this is, we divide basically with the partition function, right? The sum over all assignments there, right? The weight for its assignment, right? What is the hardcore model? Given some graph G, the hardcore model is a distribution over the dependent sets of G, right? What is an independent set? Is a subset of vertices that does not span any edges, right? So we have this parameter lambda. Usually we call it fugacity. Will, I think, called it activity. There are various names for this one. I call it fugacity. So hardcore model states that the independent set sigma gets probability measure mu sigma, which is equal to fugacity rise to the size of independent set, right? And divide with the partition function, right? And we have been discussing yesterday about algorithms that estimate this partition function, right? If you remember. So in this talk, we are going to focus, we described, I guess, in detail, this Weitz's deterministic approach to estimating the partition function. Today, we mostly focus on randomized algorithms, right? We are going to discuss about FPRAS, right? So what is an FPRAS? If FPRAS stands for fully polynomial time randomized approximation scheme, right? And basically, FPRAS is any algorithm that computes an estimation z hat of partition function. Say here it's for the hardcore model, which is within a factor 1 plus minus epsilon from the actual value, with probability at least 1 minus delta, right? We have probabilistic approximation guarantees, right? And we get this estimation in time, which is polynomial in n, the size of the underlying graph, 1 over epsilon and log of 1 over delta. Right, and as we said yesterday, the randomized algorithms focus on generating approximate samples from the Gibbs distribution so that they estimate the partition function, right? And today we are going to see the Markov chain Monte Carlo method. We are going to use the Markov chain Monte Carlo method to generate approximate samples from Gibbs distributions. Particularly, we are going to use a well-known Markov chain. We saw the definition yesterday, but it's good to recall this one here today. We are going to use Glauber dynamics, right? So this is a discrete time Markov chain. The configuration space is the support of the Gibbs distribution we want to sample from. So if it's the Ising model, then it's assignment. The configuration space is the assignments of plus minus 1 of the vertices of the graph. If it's a hardcore model, it's independent sets, right? And the Glauber dynamic is set up so that it converges to the Gibbs distribution we want to sample from, right? Of course, we need to have some technical condition here, which is called ergodicity. But this condition is trivially satisfied for at least for hardcore model and the Ising model, right? So convergence is never an issue here. So how does what is the transition rule for Glauber dynamics? Suppose that at time t minus 1 we are at configuration x sub t minus 1. So we get x sub t, the configuration time t. How? Step 1, we choose uniformly at random a vertex from G, right? Then step 2, for every vertex different than the vertex we chose, every vertex W, we have the same configuration as what we had from time t minus 1. And for vertex V, at step 3, we update the configuration according to the Gibbs marginal at V, conditional what happens at the neighborhood, right? And sorry, and we also saw yesterday this example, right? So we have this star graph, right? And suppose that at time t we update vertex V, right? So if then how does the update rule works here? So if none of the vertices 1 up to 8 is occupied, is in the dependent set, then x t sub v becomes member of the dependent set, becomes occupied, as we say, with probability lambda over 1 plus lambda, where lambda is the fugacity, right? If you remember. So if there is a vertex in one of the arrays is occupied, then of course x sub t cannot become part of a dependent set, right? So x sub t is occupied with probability 0. So is it clear what we are doing here? Okay, so what is the idea? So the larger t, the closer the distribution of xt is to the distribution we want to sample from, right? So now the idea is somehow to have an algorithm that simulates the Markov chain for sufficiently large number of steps, right? So, and then in this setting, somehow, what, like if you want to study the efficiency of the algorithm, the measure of efficiency is how fast the Markov chain, Glauber dynamics specifically, converges to equilibrium, right? What is what we say the mixing rate? And a measure for mixing rate of Glauber dynamics we use here. There are many different measures. Is the mixing time, right? And what is the mixing time? So it's mixing time is the number of transitions t, the minimum number of transitions t, such that the configuration of Markov chain after t steps, regardless of what was the initial configuration, sigma, is within total variation distance 1 over 1/4 from the equilibrium distribution, right? This total variation distance is essentially L1 distance, right? Divided by 2, basically. right? And for our purposes, we would like to have mixing time, some small polynomial of the size of the graph, something like n squared or n log n, perhaps, right? So another notion we discussed yesterday is not only in my talk but in various talks is this notion of tree uniqueness, right? So just to remind you, what is the tree uniqueness? Suppose that this is a tree, delta regular tree for some integer delta, right? We want to, and we have some Gibbs distribution on this tree, maybe the Ising model, maybe hardcore model. Now what we want to do is we want to compare the Gibbs marginal at the root with the Gibbs marginal at the root, where we at distance h from the root, at level h, if you like, of the tree, we impose some boundary conditions sigma, right? We want to compare these two marginals in L1 distance, in total variation distance, and particularly we want to compare them as h tends to infinity, right? To have this nice limit here, and as turns out, this limit has two possible values, right? It's either 0 or it's some quantity delta bounded away from 0, right? Now we say that we are in the uniqueness region for the Gibbs distribution, or in the tree uniqueness, if you like. If for any configuration sigma, this limit is 0, right? Otherwise, we are in the non-uniqueness. Right? Non-uniqueness means basically for our distribution that we have long-range correlations, right? So meaning that configurations at level h, regardless of how large h is, somehow have non-trivial effect on the distribution at the root. Right? So, for example, and one celebrated result in the area from 80s is the uniqueness, non-uniqueness phase transition for the hardcore model on the delta regular tree. Right? We have this critical value, lambda critical of delta, which is this quantity here. Right? And which essentially implies that it says that if lambda is smaller than lambda critical delta, then on the delta regular tree, you are in the uniqueness region. If your lambda is bigger than lambda critical delta, then you are in the non-unique. Right? There is a similar bound for Ising model. We are going to see it a few slides later. Okay. So any questions with this stuff? So most of the material has been covered, perhaps in faster pace yesterday, but is there any questions so far? Okay. So just let me remind you from Will's talk that somehow there are some hardness emerging in the tree non-uniqueness region, right? So yeah, basically, when we set the parameters of the Gibbs distribution in non-uniqueness, then there are instances that somehow it's computationally hard to approximate the partition function, right? And for the counting problem. And in the uniqueness region, we also discussed White's algorithm, right? Which is an FPRAS, a polynomial algorithm, right? And also we saw something about FPRAS, right? If you remember. Okay, let's see what we have for FPRAS, because this is going to be important component today. So we have this result, fix some Gibbs distribution, which can be a hardcore model or the Ising model, right? Fix the parameters so that we are in the uniqueness region for the delta regular tree, right? Then for any graph G of maximum degree delta, the mixing time of Glauber dynamics for mu specified for the graph G is big O of n log n. Right, so this tells us that somehow the Glauber dynamics mixes fast and actually mixes has the best possible mixing time. Right, asymptotically you cannot improve this n log n. right? And this beautiful result is basically comes from these three papers by Anari, QQ, Oveis-Gharan, Chen, QQ, Vigoda, and Chen, Feng, Yin, and Zhang. And this Chen is different person. Right? So if we go back now in our scheme, in the hardness, discussion about hardness. So basically what we have is that in uniqueness, we not only have this Weights is beautiful algorithm, but we also have rapid mixing for Glauber dynamics to do counting. Right? So let me remark here that when we have hard instances, we don't expect the Glauber dynamics to mix fast, right? Because otherwise the problem is not hard, right? So hardness somehow also implies slow mixing for Glauber dynamics, of course. Any questions here? Okay. So in order to proceed, now let's step back a bit, right? And let's try to see what we are trying to do, right? So this whole discussion I've been showing you so far is basically I'm trying to make a case and somehow try to distinguish cases where mixing for Glauber dynamics is fast and cases where mixing is slow, right? And I have this very nice division: uniqueness, non-uniqueness. Uniqueness, everything is beautiful. Non-uniqueness, everything is hard. Things can be hard, actually, right? And actually, what is interesting here is that these regions, uniqueness, non-uniqueness, are specified with respect to maximum degree, right? So these are somehow parameterized and are functions, these regions, the maximum degree of the graph, right? Because recall that we use the trig uniqueness for the delta regular tree, right? And somehow also we have to keep in mind that this bound somehow is hard in the sense that in this region, we really have hard instances, right? So not everything is hard, but we have some hard instances. So unless, of course, not sure, will P and P equals RP. This hardness is conditional. P equals RP. Yeah. So this is unlikely. So yeah, there must be some hard instances here, right? Okay. Now in this in view of these things, I'm start wondering, can we do anything better? Of course, better. I mean, I'm trying to be serious here, right? So I don't want to solve any. I don't suggest solving a P versus NP problem, right? So no phone calls to Clay Institute prizes and so on. Not here, right? So yeah, basically, what I'm thinking here is, okay, in the non-uniqueness, we have some hard instances, but are all instances hard here? Is it possible to find some other instances that the mixing is fast, even though we are in the non-uniqueness? Actually, there are some cases that families of graphs that this is true. So, but I'm going to find some general principle here, right? So to phrase it in different terms, so I'm thinking of classifying what mixes fast with what mixes slowly, but using a different parameter than the maximum degree, right? Of course, I have to be careful here, right? So hardness is present. So at some point, hardness should kick in, right? I cannot, I don't want to do this, right? And in general, the moral of this thing here is I'm trying to have a final classification for the problem, right? I'm trying to have a more precise dichotomy of what mixes fast and what mixes slowly. So are my objectives clear? Okay. So what I'm suggesting now is that replacing the maximum degree delta with the spectral radius of the adjacency matrix, right? So let's start with what is the adjacency matrix. I guess that most of you have seen it before, but make sure that everybody is in the same page. Let me repeat the definition. It won't take you long. If we are given a graph G, right, we define the adjacency matrix, this calligraphic A sub G. So this is a 0-1 matrix, and this is indexed by the vertices of the graph, right? And the entry UW, for any two vertices UW, the entry is 1 if the vertices are adjacent, and it's 0 otherwise. So is it clear what is the adjacency matrix? So adjacency matrix is one of the best matrices you can hope to encounter in your life, right? It's symmetric. It's really beautiful, right? So spectral radius. What is spectral radius? So if theta 1, theta 2, theta b are the eigenvalues of the adjacency matrix, I just pick the largest eigenvalue in magnitude, right? So equivalent, you can just choose the maximum eigenvalue. It doesn't make any difference, of course. Actually, for all the matrices I consider here, and I mentioned the spectral radius, but you feel free to change the spectral radius with the maximum eigenvalue. It's the same thing. Our matrices are beautiful, right? Okay. So how are we going to do it? We are going to use this newly introduced method, spectral independence, right? And yeah, we have seen some definitions yesterday, but let's go through some of them in a slower pace. So at the core of the spectral independence, we have this notion of pairwise influence matrix, denoted by I sub j, right? So this matrix is specified with respect to some Gibbs distribution mu, right? Is a matrix whose entries are in the interval 0, 1, and it's indexed by the vertices of the graph, so similarly to the adjacency matrix, at least this version here, right? And the entry I of WU is this quantity here, right? So what is this quantity here? So suppose that this is our graph, right? So we study how changing the configuration at W affects the marginal distribution at V, right? In terms of L1 distance, in total variation distance, right? Oh, sorry. So this is what this total variation distance stands for, right? And usually the number, this entry here, it's usually called the influence of W on U here, right? Of course, we can extend the notion of influence matrix when we have this conditional measure, right? Some region lambda, the graph, we impose some condition tau, right? So then we can always, you can have this influence matrix here, the same way as before, but here we have the conditional measures, and now the influence matrix is indexed by the vertices outside the lambda. Just some small detail, of course. So is it clear what is the influence matrix? Okay. So we saw the, okay, so having defined the influence matrix, now we have important notion, the spectral independence, right? So it's important notion that actually the method gets the name from this one, right? For some real number eta, we say that the Gibbs distribution mu, sorry, is intraspectrally dependent if for any choice of lambda and eta configuration at lambda, the spectral radius of the corresponding adjacency influence matrix A sub G of lambda tau is at most 1 plus eta. Right? Now we have this celebrated result by Anari and al., which says that if your measure is mu is eta spectrally dependent, then the corresponding Glauber dynamics from sampling from mu has spectral gap, which is at least this quantity here. Right? So basically, if you do the calculations and you translate from spectral gap to mixing time, this is roughly implies mixing time n to the eta plus 1. Right? And eta typically is huge, so we have some polynomial mixing time when eta is a bounded number. Right, so this is a very important result by which basically is, this paper is that they introduce spectral dependence. Yes, yes. I mean, we can be whatever, but it makes sense to when we eta is small. In this talk, eta is preferably to be theta of 1, independent of the size of the graph. Right? And now so this bound for mixing time has improved substantially. So there has been intense study and effort to improve this result, right? And the very early result I showed you for mixing time is a good result in the uniqueness. Basically, is the outcome of all these efforts, right? But let's see another example here for the bounded case. A paper by Chen, Q, Vigoda, which shows that if you have fixed eta, right, and mu is eta spectrally dependent, then Glauber dynamics for sampling from mu has mixing time big O of n log n. Yes? So, yes, and actually it's horrible. Okay. Yeah, this is why we have bounded degree. Right, but somehow, yes. So I'm not precise here, actually, right? So, but if you are bounded degree and eta is a fixed number, then I'm more or less 99% accurate. Just to, not mathematically, but to get to convey the idea, right? And yes. So what I was saying, yes. Right, so spectral dependence, if your eta is bounded, then basically implies mixing time n log n, right? And what this earlier result I showed you before, somehow how is it derived? Basically, in uniqueness region, you can find fixed eta that the corresponding Gibbs distribution mu is eta spectral dependent, right? Okay. Yes. Please, please, please. I think what follows should answer partly what you're asking, but if you are not fully satisfied, please let me. There are more things to say. I don't say that for the economy of time, and perhaps can get too intuitive for a talk. But I'm happy to share my intuition with you after the talk. All right. Okay. Okay. So. Okay. So how do we establish a result like that, right? So basically, the natural way turns out to be that to bound the spectral radius of the influence matrix by using the infinity norm of the influence matrix, right? Infinity norm of matrix mu is what? We look the absolute row sums of mu, and we pick the largest one. This is equal to this norm here, right? Now, how do we bound this norm? Okay, this is more or less known to everyone who has worked with matrix norms and spectral agencies, right? So how do we bound this norm? Like, why this is natural thing? So we're going to see an old friend, right? We're going to see the tree for self-avoiding walks now, right? So what is the tree of self-avoiding walks? I guess, I hope you remember something from yesterday, right? So given some graph G and some vertex W there, we consider tree of self-avoiding walks. T of W basically is some kind of topological construction we create from the graph, right? And we consider walks in the graph starting from vertex W, and these walks can be either self-avoiding, meaning that vertices do not repeat, or there can be the V0 VR can be a walk such that V0 VR minus 1 is self-avoiding, and the last vertex R can repeat, right? And for each one of these walks, we have a vertex in TSO, right? And so this is a vertex set of TSO. What is the edge set? So two edges in the TSO are adjacent if the corresponding walks are adjacent, meaning one extends the other, right? And we saw yesterday this example. We have this graph A, right? And this is TSO that is generated from vertex A, right? So, and also, if you remember, I call these vertices here copies of vertex A or copies of vertex B, right? So this means that this copy of vertex D means that this vertex here corresponds to a self-avoiding walk from A to D, right? And I have this nice construction, right? And also what Weights did, so basically he given some Gibbs distribution mu G at G, right? He created this Gibbs distribution at TSO with the same specification. For example, if this is a hardcore model, then we have a hardcore model in the tree, right? But we impose some boundary conditions with some systematic way, right? And what happens now? We have that the marginal distribution of the Gibbs the marginal Gibbs distribution of the graph G at C is the same as the marginal distribution of the measure of the tree, the marginal distribution of the measure at the tree at the root C. We had this very beautiful connection from Weights. Now we deviate a bit. We look influences matrices in these two measures, right? So we have we define the influence matrix at G, but nothing prevents us for defining the influence matrix here, right? And these two matrices have this beautiful relation shown by Chen, Q, and Goda, which let me draw the instead of reading, right? So suppose that we want to find the influence of vertex V on vertex E, right? So this lemma, this nice lemma here tells you that, okay, take the measure in the tree, right? And then look the influence of the root A to the copies, to all copies of vertex E in the TSO, right? So basically, the influence of A to E is equal to the sum of influence of A to all copies of vertex E, right? And now, okay, so this is a nice reduction, but why it is useful? So recall that we try to bound the infinity norm of the influence matrix, right? So basically what we would need to do is for every vertex A, the graph, we want to bound the influence it has to all the vertices in the graph, right? So this corresponds to the 8th row of the influence matrix, right? So this means that in the tree, I need to do the influence of A to all vertices in the tree, basically, right? From this previous reduction, right? And then why this is nice? Because now we can just start playing this game with recursions, right? Tree is much easier to work with, right? So the setup is reminiscent of what Weights was doing, right? So we have the ratio marginals at the root, right? Probability of the root being plus over probability of root being minus, or probability of root being occupied over probability of root being unoccupied. Yes. There is no influence of a walk on another walk. There. Yeah. So this is the measure. This is the measure of. This is the measure of. This is the influence matrix of this measure here. Right, and this VW refers to vertex of the tree. Right, so this means that. So in this example, W is vertex A. Right, so here I have WA, and then here I have W copy of A, and this V variable V, the sum varies over the copies of U. For me, U is E, right? So copy of E. So vary of these copies here. Make sense? Okay, cool. Other question? Okay. Okay, so I have the ratio of marginals, right? So what I'm working here really is the log ratios, not really the ratios, right? And I can set up some nice recursive relation, express the ratio at the log ratio of the root using this function H as the ratios of the subtree that hanging from the root. This is very easy to derive, but I won't do it now. I won't even show it you how this function looks like. It's not necessary, right? And what happens is that the sum of the influences from the root to all vertices in the tree basically can be expressed recursively with this relation, right? So I take the gradient of H and take this. This is an inner product here, right? The gradient is evaluated are these values here. So what this vector here is, maybe I can draw you a picture. So the first component is the influence. Here, this is influences, right? So this is the influence of B to the vertices that hanging from B. In this subtree, right? I forget this, the rest of the tree. The second component of this vector is influence of C to these vertices here. And third component, similarly, this one here. Right? And I take the inner product. Clear? Okay. So what I want to have at the end of the day in this recursive relation is that I want to find some norm for the gradient of H that is smaller than the growth rate of the tree, right? And worst case, the tree is delta regular, right? And basically, we want to find a norm that this is smaller than 1 over delta minus 1, right? And if you do this, if you just go to do this exercise, basically, you're proving strong spatial mixing, or because we know that strong spatial mixing is uniqueness, you prove uniqueness for your measure also, right? And this is how you get so this condition gives you bounded infinity norm for the influence matrix, right? And coincidentally, this condition also gives you strong spatial mixing, right? So this is why we have good mixing times in the uniqueness region, right? So basically, everything boils to the same condition. Is it clear what we're doing? Okay, so how can we improve this thing now, right? I'm going to show you two approaches. So one is actually it's quite elementary how to do it, right? So there's no much effort. So someone can show that this relation holds for the influence matrix, right? So this inequality between matrices is the entry-wise inequality, right? And these matrices are the same dimension, right? So and this side here I have what? I have this sum of L from 0 up to N. I take the infinity norm of the gradient of H and multiply with the adjacency matrix and rise to the L, right? Just looking, I'm not doing anything particularly clever here, right? But so if you are willing to believe this one here, then we have this thing, this very nice phenomenon, which is actually quite elementary, that if your gradient of H has infinity norm, which is at most 1 minus epsilon over rho, the spectral radius of adjacency matrix for any fixed epsilon, then from this relation, you immediately get that the spectral radius is at most epsilon to the minus 1, which is bounded number, right? So this gives you immediately a new way of this relation, a new way of bounding the spectral radius of this guy here, right? So how can we prove this thing? So this is, we have to get into some details. So basically, suppose that now we do the reduction from the, we have this matrix, sorry, we have this matrix here for the G, we do the reduction to the tree, right? And then suppose that I'm at the tree and I want to see what's the influence of vertex A to vertex F in the tree, right? So I can find, for each vertex on the path, B, E, D, I can find quantities, H of RB, H of RE, H of RD. This RB is the ratio of the marginal. So this is the function of the ratio of the marginal here in the subtree. Another ratio of the marginals here for H. And H is some partial derivative of H, nothing more than that. Now, if I have these quantities here, the influence of A from A to on F is basically the product of this guy, right? So this is basically, you can derive from this relation with the gradient, this recursive relation, right? And then what do I do? Say I want to see, get an upper bound for the influence of influence for the entry AE in the influence matrix of G, right? I take the T-SO starting from A. I want to sum the influences of A to the copies of E. Say I have this quantities HRB, HRE, take the product, found the influence here, HRC, HRD, HRE, you found the influence here, right? But instead of doing this, I substitute all these H of RBs with these H zeros, right? And these H zeros are the infinity norm of H, of the gradient of H, right? Nothing more than that. This means that now, of course, the H0 is bigger than HRB, of course, right? So, and the influence of A to each copy of vertex E is H0 rise to the distance of A from E, right? So in order then to bound the influence of A to E, basically I have to find a bound on the number of copies of vertex E I have at its level L in the tree, right? And then you can elementary argue that the number of copies at each level of L of the tree is adjacency matrix rise to the L and take the entry AE, right? It's some elementary thing, right? If you plug these things down here, you get exactly what we had before, right? Almost elementary, right? And then basically, if you just by just this essential observation, you can get this thing for this result, this rapid mixing result for the Ising model, right? So we have some graph G whose adjacency matrix AJ has spectral radius R for some R bigger than 1. I have mu G, the Ising model on G, which is in this region here. This region here corresponds to the Gibbs uniqueness of the R RE tree. Suppose that we have some R is not integer necessarily, but suppose that it was an integer, then this is the uniqueness of the R RE tree. Its internal vertex has R children, right? So this is the uniqueness region for the Ising, right? So if you have Ising model and beta in this region, then Glauber dynamics on mu G has n log n mixing time. Any questions here? Anything. So yeah. So basically, from this side up to 1 is a D ferro, and I think from 1 to this bound is ferro, or the other way around. Okay, so this interval includes 1, which signifies the ferro and the ferro. It's the formulation is a bit different than perhaps you e to the beta, right? Any other questions here? Okay, so how about other distributions? How about hardcore model now? So it turns out that this condition for the gradient of H is too strong, right? Ising model is not so amenable in metaphorical sense here to this kind of tricks. It requires something substantial to prove rapid mixing, right? Ising model in this sense is easy, right? Okay, so basically we have to go back to talking about matrix norms, right? So what I talked before is involves some topological tricks doing, but now we'll go back to matrix norms, right? And yes. 5 minutes would be okay. Okay, so I'm using this matrix norm here for the influence matrix. So what is this matrix norm? Basically, I have this matrix D, right, which is a diagonal matrix, and the diagonal has the entries correspond to the entries of the principal eigenvector of the adjacency matrix, right? And I assume, of course, that the matrix, the graph is connected, so the components here are strictly positive, right? And I multiply the influence matrix from the right side with D raised to 1 over Q. Q is some number at least 1. From the left side, I multiply with the inverse of this matrix, right? And I take the infinity norm of the product, right? And if you do this, if you take this, of course, since this is, you can argue that easily that this is a well-defined matrix norm, and so this is an upper bound for the spectral radius of the influence matrix, right? And then you can show this thing for the hardcore model, right? So now what here is maximum. So here what I have is suppose I have a graph G of maximum degree delta. Now delta must be bounded, right? And suppose that the adjacency matrix has a spectral radius R, which is at least 1, bigger than 1, sorry. Right now, if you choose a hardcore model with fugacity lambda, which corresponds to the uniqueness region of the hardcore model at the RRE tree, right? Then the mixing time of Glauber dynamics for UG is at most is big O for n log n, right? So, any questions here? Yes. I think yes. It depends only on epsilon. Yes, if I remember correctly, but I can double check. Maybe wrong. So I don't have much time here to talk, but somehow why this is useful, why this makes sense. Have to start working the analysis we had before, but we have to involve potential functions, right? So the analysis is way more involved, right? And typically this is what happens when you move away from the infinity norm of the gradient of H. But also, what happens with the potential function is that somehow you're doing some amortization, and this means that it makes sense to start thinking about the influence of one vertex to everybody. So this is why you end up using some infinity norm here, right? So, sorry. So yeah, what I'm doing here, let me show you quickly what I'm doing. So basically, when you apply the norms, it's quite involved, but the idea is that with the potential function is that when you have this H of RB, H of RE with the influence, you do the amortization is as follows. For say vertex E, instead of having HRE, you cut this HRE to halves, square root of HRE, square root of HRE, move one HRE here, right? And here you get square root of HRB from the parent. And this is a kind of amortization that you get. And somehow this works nicely because the system is a different magnetic, right? So it's way more technical, but this is the essence of using potential functions, right? And basically, then because you consider huge groups of vertices, somehow in order to give rise to dependencies on spectral radius of graph, so you have to, when you look the vertices on this level L, you have to introduce some more extra weights, right? So for vertex D, the copy of vertex D, you put the component D of the principal eigenvector rise to 1 over Q, right? And similarly for F, E, B, and A. And Q here is the same Q as the norm we look for granted, which some Q is very complicated quantity, right? So then basically here we start by looking this weight here, right? And we work inductively up, right? Actually, you have to basically this setting gives rise to using this standard relation we have for the entries of the principal eigenvector, right? The sum of the components, the neighbors of vertex W is equal to the spectral radius times the component W, right? So we also need to put some weight here in order to fix things and make the whole computation like give rise to matrix norms. And this weight here is basically what destroys us for using unbounded degree, right? This is a technical problem. Okay, so conclusions. So we give some new bounds for mixing type of Glauber dynamics for hardcore model Ising model. So the problem, the actual use of spectral radius has been studied before. So I'm not claiming that this idea is mine, but it was used by using some much weaker techniques for proving mixing time. So this spectral dependence is a really strong method, so it makes sense to try these ideas here there, right? I can give you I can describe you later if you like the improvements I get with respect to the previous approaches. So we saw two approaches for establishing spectral dependence and hence mixing, rapid mixing. It's like this some topological trick, this elementary trick I showed you before, and we use some new matrix norms. So what I told you here is mostly good results, right? Positive results. So what happens with negative results, right? I would like to have the distinctions of hardness and efficient algorithm with respect to spectral radius. I only show you the good news, so maybe someone can give us the bad news. So yeah, there are some results from early 2000. It's notoriously difficult to actually establish this kind of hardness result. So plenty room for improvements here. Anyways, thank you very much, and sorry for the delay.